Hello, everyone. Welcome. Thanks for joining. So first of all, this is the second time that I've on this conference. It's a great conference. For me, it's the perfect size of a conference, like this mid-size conference, because you get to talk to other people, you get to meet other people. They're not too small, they're not too big, but they're very, very difficult to organize because usually they're community-driven. And it takes a lot of love and a lot of work to make that happen. So I want to please give a big round of applause to Ricard and the rest of the organizing team, because they've done it very, very well again. OK, so my talk today is called A Tale of Latency. My name is Pulido. I'm trying to move away from the other side, social side, to this new one that probably is going to get the new community. So if you want to follow, I'll follow back. Let's try to build a community there. I work for a company called Datadog. This talk is not about Datadog itself, but just to know Datadog is a platform that helps companies improve the observability and security of their infra and applications, including, of course, Kubernetes itself, but also the applications that you're going to run on top. But I think the important thing here is the subtitle of this talk, which is Understanding Kubernetes CPU Requests and Limits for Sustainability and Profit. And I think that those two words, sustainability and profit, are the key ones, because all of this would be a lot less interesting if energy was free. Free in the sense of it doesn't cost money, and free in the sense free from the environment, like it doesn't cost anything bad for the environment. And unfortunately, none of those are true today. They might be in the future, but definitely not today. So this is something that all of us should pay attention to. So when we talk about requests, CPU requests and limits, in Kubernetes, when we are basically talking about this abstraction when we define our workloads in Kubernetes, this section when we have resources, and we have some requests and some limits for CPU memory and queue pages and other things. So this is what we are going to be talking about today. We are going to be talking about this abstraction and how it translates to some of the things internally. For this talk, we are going to be focusing on CPU only. The reason is memory is a completely different thing. Even though they share the same abstraction in Kubernetes, like this section, what happens afterwards is completely different. So probably memory will be a complete different talk if I wanted to do one. So picking those numbers, picking the values that you choose for your CPU requests and limits is called sizing your workload. And picking the right ones is what we usually call right sizing. And why right sizing is so important? Basically, in terms of CPU, if you pick a number that is too low, you're probably going to get throttle at some point. You're going to get your performance degraded at some point, and we are going to see how and when that is going to happen. If you do the opposite, if you pick a number very, very big, that's going to increase your cloud costs. And obviously, you're going to have a lot of energy waste in return. And right sizing, we are not doing it quite right yet, because it's very difficult to do. It's not like a simple science that you apply a formula and you get it the right size. It's a little bit more difficult than that. So these are numbers from Datadog customers that we collect and we anonymize, and then we track some data out of it. This graph actually is from a couple of years ago, but things haven't changed a lot. So you can see that a lot of containers are using a lot less than they requested, so they are wasting a lot of CPU. But also, a lot of them as well, like 10% of them, are using more than double than they requested. And we are going to see why is this possible. And you can see nothing in the middle. This distribution should have basically the opposite area, and we don't have nothing in the middle. So this talk is about how you, as developers, can try to make this a little bit better, how you can find ways in which, at least for your applications, move to that middle section instead of being on the edges. So let's start by talking how CPU requests affect Kubernetes scheduling. And I think this is the thing that is most commonly known when you start using Kubernetes. This is very simple as an abstraction, and also it works very, very similar. It works the same with memory. It's the one thing that works the same for both memory and CPU. But before we go deep into that, let's think about how those VMs, those nodes, get filled up with pods, which is basically scheduling your pods into the different nodes. When we think about that, we usually think that this is what happens. Like, you have a VM running probably Linux, a container runtime, and it's attached to your cluster. It becomes a node in your Kubernetes cluster, and you start scheduling pods into there until it fills its capacity. But actually, that VM needs to run a Linux kernel. It needs to run system processes. It needs to run Kubernetes processes that are not containerized. And therefore, the capacity is a little bit less than that. The problem is that Kubernetes doesn't know about the capacity of the things that are not containerized. So a trick to tell the kubelet that the capacity of the node is a little bit less is by using these two parameters in your kubelet. Basically, you're telling the kubelet, I'm going to reserve maybe 500 millicore for my Kubernetes processes and 500 millicore for the system processes, for example. It's like numbers that you set up manually. Again, another layer of sizing, in this case, your node, to make sure that the scheduler knows that there is something else running there that needs compute as well. We also have this eviction threshold, which is a value in memory. It has a default on 100 megabytes. And basically, it means that when the node reaches that capacity, like before it fills up out of memory, start evicting pods. That's what is called the eviction threshold. So that also reduces the capacity of your node. And the actual capacity of your node is what we call in Kubernetes allocatable. This is a value you can find in various metrics when you describe your node, so it's very easy to know exactly what is the capacity of your node. That said, let's go a step back, and for the examples that we are going to see on this talk, we are going to ignore those things, and we are going to think that allocatable is a full node, basically for simplicity's sake. So how does CPU request translate to that Kubernetes scheduling? Again, I think this is the part that is mostly best known. Let's imagine that we have two nodes. Each node has two cores. And we create a pod that is requesting 1,500 millicore. So the Kubernetes scheduler is going to try to find a node that has enough capacity. And basically, it goes through an algorithm of things that it has to match. But in terms of capacity, it says, OK, node 1 has enough capacity, so I'm going to place it there. And it goes and places it there. And then we create a second one that is requesting a full core. And the Kubernetes scheduler is going to do the same thing. It's going to say, OK, I'm going to see if node 1 has enough capacity. I only have half a core left. So I'm going to place it on node 2. And this is all fine. We have a situation here where we have the first node filled up with 1 core and a half, waiting for a pod to be created with requesting less than half a core to be placed there, the other one with 1 core. But we are assuming that these pods are right-sized. But what if they are not? What if, for example, the container on pod 1 only needs 0.25 cores, and the other one only have a core? So suddenly we have a lot of space that is both unused and unschedulable. So the problem with that is now the problem is a lot more apparent because we have a lot of space that is not being used, a lot of CPU that is not being used, yet we cannot schedule anything bigger than half a core, for example, on the first node, even though there is enough capacity. Like, it could happen, but that's the way the scheduler works. So CPU requests are not only used for Linux, for Kubernetes scheduling. That's where people understand, but it's also used for actually giving time, CPU time, to your workload. Giving is what the complete fairly scheduler in Linux does. So like basically distribute CPU time among the different workloads. And the thing is that the Kubernetes team decided to use the same CPU request abstraction that they were using for Kubernetes scheduling to translate that into CPU shares, which is the thing that the CFS uses to distribute time. So basically, that same number is used for two different things. So how this is going to work in practical? So let's imagine that we have 3 pods. They're requesting 200, 400, and 200 millicore each, and they don't set any limits. It's like we just set requests, no limits. We have a single core, a single node with a single core in our cluster, very small cluster. And the Kubernetes scheduler is going to say, fine, all good, I'm going to place them all in the same node. And this is how things look from a Kubernetes scheduler point of view. So now these pods, these containers start running. They start running, they start requesting CPU. And that CPU time is going to get 100 milliseconds chunks or time slices on the CPU. And that's how the kernel is going to start distributing. By the way, this 100 milliseconds is the default, but you can change it in the kernel if you want. So let's imagine this situation. Again, we haven't set any limits. The container on pod 1 is idle, is maybe doing some I/O, is waiting, it doesn't need any CPU on that time slice. Pod 2 is requesting half the time of that CPU. And pod 3 needs 40 milliseconds, or 40% time of that CPU. And this is because we haven't set any limits. This is totally fine. Because if there is no contention for the CPU, because the Linux kernel is going to say, run as much as you want. Like, I still have 10 milliseconds idle. Please do whatever you need, and you're going to be fine. So when there is no contention, CPU requests really doesn't matter that much for that CPU time. But when there is contention, so when all the pods and containers start filling up that CPU, the way the CFS is going to do is based on the CPU shares, we are going to assign time proportionally. And because container on pod 2 requested double the time, it's going to get double the time of CPU. So in that case, suddenly, pod 3 that was able to run 40 milliseconds is no longer able, because proportionally, it needs less time than pod 2. That's why right sizing is always very important for performance. For performance, we have this concept in Kubernetes that we're all very afraid of, which are noisy neighbors. And you can have, basically, noisy neighbors is containers that are placed on the same pod, on the same node that your application, and they use a lot of resources. Like they are CPU bound and use a lot of CPU, they use a lot of networking, they use a lot of memory, et cetera, et cetera. But in the case of CPU, and CPU only, those noisy neighbors are only that noisy if we are not right-sized. Why is that? So for that, I'm going to put some examples that you can, if you want to follow. I created a very small application and a small tutorial that you can follow using a k18n cluster. So all of this that I'm going to be talking about, if you want to run it yourself, you're able to so. But basically, the application is very simple because it just tries to put these things into an example. You have a web app with a single endpoint that basically calls to downstream services. When it's called sync service, basically you have to wait for the response of the sync service to get the response back to the user. And then you have an async service that is basically in a fire and forget kind of mode, like it mimics Think of an async service, a downstream service with a queue, something like that. And both async and sync are very CPU bounded. They use a lot of CPU. So we start with a situation when they're all running in isolation. We have our application running in the node, and we are the only application that is running on the node. We are happy, all is good. We have a latency that we can control, and we are happy with it. That's the thing us, as developers, control our application, our latency of the application, etc. But suddenly, some other team that we cannot control, using a different application, they get deployed into the same node without us controlling that. And of course, we don't know why and when that is going to happen. The only thing that are the values of the things that we control, which are the latency of our application. And we can see that the tail latency of our application is starting to increase. That's like the warning sign that something is going on. And we can complain and say, OK, we see the pods that are running on my same node and say, OK, this is because we got noisy neighbors. But actually, those noisy neighbors are right-sized. Like, they requested 1 core each, and they're using more or less 1 core each. So they are the ones doing the things right. And our application, that is CPU-bounded, is actually using 5 times or 4 times, depending on the service, more than we requested. So it was our problem in the first place. If we were right-sized in the first place, that wouldn't happen, at least that much, because, again, what is going to happen first is that you have Kubernetes scheduler to make sure that you have at least guarantee what you requested, but also, in terms of contention, you're going to get proportionally CPU time. So how you can see that this is happening to your application? So there are 2 metrics that you can use. One, we got that metric from the kubelet directly, which is usage core nanoseconds. It's called Kubernetes CPU usage total in Datadog. But basically, the number, of course, that your application is using at any point, single point in time. And you can plot that against another metric, which is queued pod container resource requests, which is the request of your container. That doesn't move. But if you plot them together, you can see whether your application is using consistently more than you requested, or a lot less than you requested, or if it's seasonable, et cetera, et cetera. So those 2 things are things that you need to track. Let's talk now about limits. So for now, we were just talking about requests. We haven't set any limits yet. And basically, Kubernetes limits translate into what we call CFS quotas. When you create a container, basically in Linux, you create a C group, and you have each C group will have a lot of config, but 2 of the config that it has is first the period, which is by default 100 milliseconds. Thanks, they use the same one as the kernel. And then the quota, which is basically the amount of CPU time that you're going to be able to use on that period until you run out, and then it gets refilled on the next period. Let's see how this works with an example. So using the same example that we had before, now we have set limits on the same containers, basically the same limit as the requests. When we were not setting limits, this situation was possible. We were able to say, OK, because container 1 is idle, and there is no contention, and I actually need, on this particular time slide, I need more CPU, I'm able to use it. But now that we have limits, this is no longer possible. So pod 2 is going to get throttle. So the kernel is going to say, OK, you already run out of quota for this particular period, and I'm going to stop assigning CPU time to you. Same thing with pod 3. And now the situation is that even though those containers needed that CPU time, even though the rest of the CPU time is idle, like we have enough CPU to assign, the kernel is not going to assign it to you, which is not ideal. But the good thing is that you are able to know if this is, when you see a performance degradation in your application, you're able to see if this is why you're getting degraded. So you have these metrics come directly from cgroup stats. One is throttle time, one is unearned throttle, and basically it's the amount of time a particular container is getting throttled and how many periods it's getting throttled. So you know more or less if it's happening all the time or only at certain peaks, etc. So the question would be, why setting CPU limits in the first place? Like, we've already seen that CPU requests are used as well to distribute time proportionally with all the containers. In an ideal world where all the containers are the right size, that would be enough, because basically you have requested what you actually need. You're able to overrun if it's needed. You're not going to get throttle. Performance is going to be better. But we are not in an ideal world, and also there's other places where you want to set CPU limits. Sometimes you don't. Like, if you think that you're right-sized and you live in this ideal world, or you have like a specific node for your application, maybe you don't need to run CPU limits. But some of the reasons to add CPU limits is when you're benchmarking your application. Like, when you create your application in the first place, you don't know how much CPU and memory is going to be needed. So you do, hopefully, you do some benchmarking. If during that benchmarking you set your limits to the same value as your requests, you're going to know very, very soon if you actually need more, because you're going to get throttled by the kernel, and you're going to get that metric that is automatic. So you know exactly while you're doing those benchmarks, and you can fiddle around with those numbers. The other reason is multi-tenant environments. So when you have a cluster that is going to be shared in a multi-tenancy, and you, as an admin, wants to distribute resources for each of those tenants, sometimes the way you do that is by assigning a resource quota to each of those namespaces. And once you're in a cluster that is configured like that, then you have to set limits to your applications. Also, it's important, sometimes you want to set up CPU limits when you're sure that you're not sure if your application is that well-sized, you're not sure if other applications are going to be well-sized, and you want to avoid being surprised without your control. When we were seeing that example of the noisy neighbors, that was completely outside our control as developers. Suddenly, our latency went up. If we had set limits to our CPU, we would have seen a lot earlier that our application actually needed more CPU, and we could have fixed things a lot earlier without having to wait that something bad starts happening. And also, if you want to run on the guaranteed quality of service, if a pod in Kubernetes has a class, it can be burstable, it can be best effort, could be guaranteed. And the guaranteed ones are the less likely to be evicted when you run out of memory. And if you want to be on the guaranteed quality of service, then you have to set requests and limits, and actually they have to have the same value. So a little bit of summary. So CPU requests will be used for the Kubernetes scheduler, but they also will be used by the CFS to assign CPU time proportionally. CPU limits affect your performance, but it doesn't mean that they will get evicted, your containers. Containers don't get evicted, pods don't get evicted because of CPU contention. They just get throttled. But actually, there is something more, talking about CPU requests and limits in Kubernetes. So one of the things that we haven't talked about yet is, like, we've placed our container, a pod, in a particular node, and now we start running. But our node has several cores, and actually our workload, our containers can run, depending on the time slice, the kernel may decide to run them on different cores. This can happen. And for many applications, for most applications, I would say, this is totally fine. But there are applications that are, they don't want context switches. They rely a lot on the CPU cache, etc., like, for example, ML training, etc. They want to run only on a specific cores. So there is something in Linux to do that. It's called CPU sets, and basically allows you to pin specific C groups to specific cores. And because basically Kubernetes is an abstraction of all these things, Kubernetes has implemented an abstraction called CPU Manager to implement exactly this. And let's see what is CPU Manager quickly and how it works. So CPU Manager is a policy that you set for your kubelet. So you can have different nodes with different policies. The default one is known, which is how Kubernetes always have been running until this existed, because this is actually fairly new. Basically, all cores are shared, and the kernel can move things around as it fits. But now we have something called a static policy. And if you run the kubelet with a static policy, that node allows workloads to pin to a specific cores. With a little bit of a caveat, this only applies to C groups. This only applies to containers. So any other process that you're running in your node can actually run on those cores. So how do you do, now that you know that your cluster, you've talked to your Kubernetes admin, they tell you that they set some nodes on the static policy, how you get access to those exclusive CPUs. So basically, you have to run on a guaranteed quality of service, so you have to set CPU requests and limits to the same value. And the CPU value on the requests and limits has to be an integer, because if you want exclusive access, you cannot say 2.5 cores. Like that wouldn't be exclusive. You have to do 2, 3, 4, the number that you need. And but interestingly, when you do that, you affect the rest of the containers that are running, the rest of the pods are running on the same node. So it's a metric to watch is this one, container CPU limit. This is a made-up one that we did at Datadog, but you can calculate it if you don't use Datadog as the minimum between the actual container limit and the host capacity minus any static assignments. And why this is important? Because let's imagine that we have this node with 4 cores, and it's running on a static policy. So containers, if they want, they can assign them to a specific pin it to a specific cores. So what is going to happen is that as soon as we start the kubelet is going to say, OK, I'm going to tell the kernel that the default CPU set is 0 to 3, like 0, 1, 2, 3. So basically, any core. We are going to get something reserved for Kubernetes processes and system processes, for example, half a core. So it's going to say, OK, actually, I only have 3 cores for specific workloads. This is only to try to do capacity planning, because actually those reserved capacity for those processes can actually run on any core. But it's more as a way for the Kubernetes scheduler to be able to do some capacity planning. And now we run our application. And our application is requesting 500 millicores and 200 millibytes. Because it doesn't have set any limits, it's going to be run on the default CPU set. So it's going to get assigned to this node, for example. And the CPU set is going to set to 0 to 3. So basically, my container is going to be able to run on any of the cores. And because we haven't set any limits, our limit really is 4 cores, the 4 cores that are available in my node. If there are no other workloads and I need a lot of CPU, it's going to run as much as it needs. So let's imagine that our application is badly sized, and it needs like 3 full cores. Like it has several threads, start using a lot of our CPU. And then we have a second application that gets it has set memory CPU limits and requests to the same value, and the CPU number is actually an integer. So it's going to get an static assignment. So what is going to happen at that point is that it's going to get assigned to the same node, and it's going to say, OK, pod 2 has a CPU set on 2 and 3, so it only can run between 2 and 3, and it's going to get exclusive. So if it uses it, if it doesn't use it, it doesn't matter. These are the cores for this container. But it's going to do something else. For the containers that are already running, it's going to say, OK, we are going to move that to the rest of the node, which is containers 0 and cores 0 and 1. So suddenly, our container was able to run and use up to 4 cores. Now it's only able to run up to 2. So by using that metric that controls the actual limit, the real limit of our application, we are able to know exactly what's going on when we get degraded. Cool. So now, yeah, we are going to finish. So my biggest takeaway for this talk would be that if you're deploying to Kubernetes, even if you're not an admin, if you're not a Kubernetes administrator, if you're a developer, if you're deploying to Kubernetes any application, knowing about CPU requests and limits and what it means and how to control them will make you a better developer and also a better citizen. Thank you.
OK, great talk again. Thank you, Ara, for coming. It's always good to have someone who understands Kubernetes and all these things. So yeah, so some questions from the audience. First one is, sorry, can you keep it low? So some people are saying that sometimes now it's recommended to not have CPU limits to prevent CPU throttling. What are your thoughts on that?
Yes, exactly. So if you, that's a strategy that you can follow. But again, you have to make sure that the applications are well sized in the first place before removing limits. You have to make sure that all the applications that are going to be scheduled with your application that are going to be co-located in the same node are also right-sized. So it's a good strategy, but you have to be careful because if you don't set limits, then you cannot predict degradation in your performance because you get those noisy neighbors around. So again, limits are great for benchmarking to predict those degradation. But once you're happy, maybe you can remove limits altogether to avoid being throttled. So as anything in computing, it depends, which is it's not a great answer.
It is what it is. So another common case is like, OK, imagine there's a pod that takes a lot of CPU on startup, but then it's stable. Like, and maybe you need to request that for startup, but then it doesn't need that. What are your thoughts on such situations?
One of the things is maybe why it requests that much. So that would be, and you can also doing things like init containers. It's because you are doing something to start up your application. Maybe you don't have to do it on the main container. You have to do it on an init container. So that would be my strategy. Like if you have a lot of startup time to think about whether that's actually part of your application, that's actually part of a different service. So you can basically try to avoid that situation as much as you can.
Then someone else is asking about comparing horizontal versus vertical scaling, like adding more servers versus adding more pods. Obviously, you have the problem of the daemon sets that will run in every server. But aside from that, what would be the sweet spot for one versus the other?
This is actually a very difficult question because as soon as my suggestion would be is that some people say, OK, if you're using horizontal scaling, the metric that you need to scale horizontally is not CPU and memory. You have to scale by request per second. I don't think so. I think the thing that your application needs is actual CPU, is memory, is not requests. So I still think it's a lot better to understand the CPU needs of your application and therefore horizontally scale your application using CPU. But the problem is that those are the two things that you use as well for vertical scaling. And as soon as you start doing multi-dimensional scaling, like you try to use the same metric to scale horizontally and vertically, especially if you do automated auto-scaling, like if you're using the VPA and the HPA at the same time, both with the CPU, it becomes a little bit more difficult because as soon as you scale horizontally, then your vertical scaler is going to go down, then you're going to, like, it never stops. So one of the strategies that people say is that is to avoid using HPA and VPA at the same time because, again, it's difficult. I wouldn't go through I wouldn't recommend like using different metrics. That for us hasn't worked at all. Using CPU and memory has worked a lot better for HPA. We actually have a talk called, if you want to check it out, we have a series where we explain how we do things at Datadog called Datadog on something. And there is an episode called Datadog on Kubernetes autoscaling. And we explain how we try to do this multi-dimensionally scaling. So if you want to check it out, that's a lot better explained than I just did there. But again, it's actually multi-dimensional is something that is quite difficult.
So someone is asking if you know of any downsides on decreasing the Linux scheduler time slots.
No, I don't know.
Okay. And then some people are asking, okay, say you have an application that it's predictable, but it's not constant. Like, how would you approach that? Would you have a process modifying the request and limits? Like, because sometimes pods need different CPU usage depending on the spike of the application. That's probably a complex scenario, but.
Yeah, well, it's a scenario that we need to account for. One of the things is, again, going back to the other question, is doing a scaling of that application. And if it's seasonable, you can control more or less when you want to do that.
So I think that covers most of them. Sorry if not, but you will be around. And
yes, I'll be around.
Before that, her city is under flooding, so hopefully she will be able to come back tomorrow. Let's cross fingers that the rain stops in Malaga. Thank you very much for coming, Ara. It's such a pleasure always to have you, and thank you very much.